Hello guys, welcome to my channel Maths Boy. I am here again to teach you Euclid's lemma and Euclid's division lemma and Euclid's division algorithm in this video. Okay. Before going to see Euclid's lemma and Euclid's algorithm, let's solve a small puzzle which is given in your textbook, right? There's this puzzle what says that a trader was moving along a road selling eggs. An idler means a guy who doesn't have any work, okay? An idler who didn't have much work to do started to get the trader into a wordy duel. This grew into a fight. He pulled the basket of eggs and dashed it on the floor. The eggs broke. The trader requested the panchayat to ask the idler to pay for the broken eggs. The panchayat asked the trader how many eggs were broken. He gave the following response. So this trader was a math geek, and so he didn't tell the number exactly. Instead, he threw a puzzle for them. Okay, let's solve this puzzle. So what he said is, if counted in pairs, one will remain. If counted in pairs, one will remain. What he said, if the eggs are counted in pairs, like two eggs as one unit, two eggs as one unit, then one egg will be left out. It will not have a pair. Okay, that's what he said. So let us transform this into an equation, no? Okay, so let A be the x, let A be our x, A be the number of x. So the number of x according to first statement is A is equal to, so he is counting in pairs, so 2 into, let's say there are B number of pairs, B plus 1 will be left out. If you count all the eggs in pairs, so you'll have 2 into B plus 1. Okay, B can be any integer depending on the number of eggs he has. Then coming to the second statement, if counted in threes, 2 will remain. What he said, if counted in threes, then we'll write this equation as 2 into, since they are counting in threes, so we'll write our equation as 3 into, let's say C, plus 2 will be left out. So since they're counting 3 as 1 unit, 3 as 1 unit, 3 as 1 unit, 2x will be left out. So had there been 3x, that can also be included into 1 unit, but only 2x we have, so that's why the extra 2. Okay, then third statement says, if counted in fours, 3 will remain. So our equation would be A is equal to, they're counting in fours, so the number of x would be 4 into something, let's take D, 4 into something plus 3 will remain, 3. Then next statement says A is equal to, counted in 5s, 4 will remain. They're counting in 5, so 5 into something, let's take E, and 4 will remain. Okay, next statement says, if counted in 6, 5 will remain. They're counting in 6, so 6 into something, let's take F, plus 5 will remain. Then last statement says, if counted in sevens, nothing will remain. 7 into G, let's take G, nothing will remain, plus 0, plus 0. Even if I add plus 0 or no, there's nothing, no? So A is equal to 7. G is the last statement. So if they're counting in 7, no x will be remaining, which means our A is a factor of 7. Sorry, A is a multiple of 7, which, and also he said that my basket cannot accommodate more than 150 eggs. So since his basket is so small that it cannot fit more than 150 eggs, so we have taken A as number of eggs, no? So A is less than 150. A cannot be greater than 150 because he said that his basket cannot fit more than 150 eggs. So the number of eggs in the basket should be less than 150. This is very important. And we also got that our A number of eggs is a multiple of 7 and A is less than 150. So two clues we have here. So let's write all the multiples of 7 which are less than 150. So our A will be set of, A can be any number in this set, okay? First multiple would be 7, then 7 2 is 14, then 7 3 is 21, then 28, and so on till 147. 147 would be the last number, okay? Which is less than 150, and of course factor of 7. Multiple of 7, not factor. So our A, number of X, is any number in this set. So how do we find the exact value of A? Which is, you should do this by trial and error method. You take 7, first number, check with all these equations if 7 can be written in all these forms or not. I'll show you. Let's take first equation. A is equal to 7 should be written in the form of 2 into something plus 1. I can write 7 as 2 into 3 plus 1, right? So first equation is satisfied. Then A is equal to second equation. 7 should be written as 3 into something. I can write 3 into 2 plus 2, but I'm left with only 1. So 7 cannot be written in this form. So 7 is not our required number, okay? You need to check all these equations with all these numbers. There will be one number which will satisfy all these equations, okay? Since I've already solved this, I know that 119 is the number that will satisfy all these equations. You can check, okay? I'll show you now. A is equal to 2 into, I can write 119 number as A is equal to 2 5s are 10, 2 9s are 18 plus 1, right? Then coming to second equation, I can write 119 as A equal to 3 into 3 3s are 9, 3 9s are 27 plus 2. I can write it in the form of 3C plus 2. Then A is equal to 4 into 4 2s are 8 and 4 9s are 36 plus 3. I can write it in the form of 4D plus 2 and so on. A is equal to, I can write it like 7 into 7 1s are 7, 4 will be left out, 4 9 49, 7 7s are 49, of course plus 0. Even if I write plus 0 or no, there's nothing harm, okay? A is equal to 7 into G, 7 into something, or I can write it as like this also. So 119 is the number. I can write this as in all these forms, okay? So 119 is the required number. Therefore number of eggs in his basket is 119. So any number A and B, if you take any two numbers A and B, then they can be written in the form of A is equal to BQ plus R. That's what we have seen here. A is equal to 2 into B plus 1, something like that, okay? So this form is obtained from Euclid's lemma. Let's see the statement of Euclid's division lemma. Euclid's division lemma states that given positive integers A and B, there exists unique integers Q and R satisfying A is equal to BQ plus R, where 0 less than or equal to R less than B. This is the condition or R, okay? So you might get confused by seeing all these A, B, Q, 1, R. So instead of this, you can also understand Euclid's division lemma by this thing. Dividend is equal to divisor into quotient plus remainder. Let's understand the statement now. Okay, let's understand with an example. So if I'm taking the numbers 2 and 9, let's divide 9 with 2. 9 with 2. So 2 4s are 8 and 1 is the remainder. So I can write 9 as 9 is equal to 2 into 4 plus 1. 2 into 4 is 8 plus 1 is 9. So I can write 9, which is my dividend, as 2, which is the divisor, into coefficient plus remainder, divisor. Okay, so if you take any two numbers, you can write it in the form of A is equal to BQ plus R, and the condition on R is 0 less than or equal to R less than B. Why 0 less than or equal to r? Why? Which means 0 less than or equal to r means r is always greater than 0 or equal to 0. It's obvious, right? Our reminder, r is our reminder. Can you get any negative integer as reminder like -2, -3? No, we always get positive integers as reminder, or we will get 0 as reminder. So that's why 0 less than or equal to r. This is understood first condition. And r less than b. Why is r less than b? What is b here? B is our divisor. Here our divisor is 2. Our reminder is 1. 1 is strictly less than 2. Here it is satisfied. Why? Can our reminder be 3? If 3, so that 3 is less than 2, then this condition will be wrong. But you can never have the reminder as 3 here. Say for example your reminder is 3 here, then you can divide it again to 1 or 2, then your reminder will be 1 again. So your r is always less than b, which is the divisor. If your r is greater than b, you can divide it again, no? So there's no point in having r greater than b. So r is always less than b. Okay, remember this condition. This is also important. So if you have any two integers a and b, according to Euclid's division lemma, it can be written as a is equal to bq plus r, where 0 less than or equal to r less than b. Of course, you can read this as dividend is equal to divisor into coefficient plus reminder. For understanding purpose, you can also remember this thing. We have seen Euclid's lemma. Now Euclid's algorithm. What is algorithm? What is Euclid's lemma? You might confuse sometimes between Euclid's division lemma and Euclid's division algorithm. So lemma is just a proven statement. It's already a proven statement which is used to prove something else. It's just a statement. Lemma is just a statement which is already proved. Then coming to algorithm, Euclid's division algorithm. An algorithm is a sequence of steps which you need to perform in exactly the same way. The sequence should be the same in order to get your desired output. Okay, Euclid's division algorithm, it's just sequence of steps. You need to perform them in order to get your desired output. Let's see what is Euclid's division algorithm. We usually use Euclid's division algorithm in finding HCF of two positive integers. Okay, let's say the positive integers be c and d, where c is greater than d. Okay, one number should be greater than d. One number should be greater than the other number. No, otherwise, how do you perform division? If you take 2 and 2, you know 2 by 2 is equal to 1. So let's take one number greater than other number so that we can find the HCF actually. So to find the HCF of any two numbers c and d, we need to follow these 3 steps. Not 3 steps actually, until you get the remainder 0. Let's see. Step 1, apply Euclid's division lemma to c and d. So we find the whole numbers q and r such that c is equal to dq plus r and 0 less than or equal to r less than d. Now don't get confused. Why here you have a equal to bq plus r, here you have c equal to dq plus r. No, they just replaced a, b with c and d. It's the same thing, Euclid's division lemma. So if you have any two integers, first you need to apply Euclid's division lemma for that two integers and write it in the form of a equal to bq plus r. Okay. Then second step, if r is equal to 0, the d, which is the divisor, is the HCF of c and d. Okay, if you get in the first step itself your reminder is 0, then d is the HCF of c and d. And if r is not equal to 0, apply the division lemma to d and r again. D is divisor and reminder. Apply the Euclid's division lemma to d and r again. Okay. Continue this process till the remainder is 0. You need to continue this process by applying Euclid's division lemma to d and r. Apply Euclid's division lemma to divisor and remainder until you get the remainder 0. Okay, when you get the remainder 0, the previous divisor would be the HCF of the given two numbers, right? You need to continue this process till the remainder is 0. The divisor at this stage will be the required HCF. Understood? We'll see with examples we'll study this Euclid's division algorithm with examples in the next video. So for this video, we can study till here. Next video, we'll solve the examples. Until then, bye-bye.